Unit 3, take 2. The material here has very little math. Unit 3 has very little math. There'll be some math today. Now, I see Celeste over there celebrating. After this unit, we have a unit that's called the mole, and it is 100% math and algebra and delicious, glorious algebra. That's right. Now don't get excited. All right. So, again, at the beginning of most of these topics, I'll have some vocab. Some of this may look familiar to you. Hopefully you recognize what an electron is, or an atom. But there are some things that I would expect you probably not be so familiar with. I will have the video linked. I'm not sure if I'm going to use this period or first period, but it will be in the content library if you should happen to need to look at it again. I know. All right. So, again, today is dealing with early atomic theory. And some of the stuff that we're discussing today should be pretty straightforward. Hopefully you've heard it or learned about it in the past here. No clicking. All right. An atom is the smallest particle of an element that retains its identity in a chemical reaction. Now, we've talked a little bit about chemical reactions in the past. I want to continue that discussion going forward here. That we are working with chemical reactions. Nuclear reactions changes the atom. In chemical reactions, the only thing that's going to change about the atom is the number of electrons. And we'll discuss that more later on, not in this topic. Although early philosophers and scientists could not observe individual atoms, we still have a very difficult time of doing that today. We could look at macromolecules, or very, very large molecules, but it's very, very difficult. We're getting closer to looking at an individual atom. But again, some of the things that make up the atom are incredibly small and misunderstood at this point. But we have some good data to support that everything's there. The early atomic theory, atoms are so small that they cannot be observed directly. Scientists could only use experimental data to help us describe the atom. Now, we do have a lot of evidence to support the things that we talk about in this class. Doing experiments over and over again with the same material and getting consistent results proves that atoms do exist. Now, some of us might say, well, I don't believe oxygen is in the air. Well, that's great. You don't have to believe it. It is there, or else you would be dead. So that's some pretty good evidence. Now, we can put you in a box and kind of like wrap it in plastic and see how long that lasts. And that would be a morbid experiment. All right, around 400 BC, there was a Greek philosopher that suggested the world was made up of two things: empty space and tiny particles. Deep thought. Okay, that's deep. But he gets credit for that. So this guy gets his name for saying that he might have been sitting like we are right now as the sun's passing through the window and saw the little dust particles and go, tiny particles. Good stuff. Fast forward 2,200 years. Not much has happened in that 2,200 years. There's a French chemist that discovered changes occurring in a closed system. We talked about this before because of the law of conservation of mass. That he stated that when he put, say, X number of grams into the box, closed it up, sealed it, allowed it to react, he got brand new stuff when he finished, but it still weighed the same. So we're still obeying this law of conservation of mass, and we'll have a question about it on the homework tonight. The law of definite proportions by another chemist states that when we look at, say, like carbon dioxide here in Plainfield, it's going to be made up of one carbon and two oxygens. If I go to, say, Avon and find a carbon dioxide, we'll also have one carbon, two oxygens. Again, deep thought there. Dalton's atomic theory. Dalton is given credit for proposing first model of the atom. And it's this right here. It's like a little super ball. Okay? In other words, his atom, and we'll talk about the model of the atom a little bit later on, is a uniform ball. There were no subatomic particles. There were no electrons, no protons, no neutrons, nothing. He didn't know about that. But he still gets credit for making the first model. And he came up with some things that still hold true today. Like elements are composed of tiny indivisible particles called atoms. Now, what does indivisible mean? Can't break it apart, yeah. Now, we can under nuclear processes, but not under chemical processes. And back in the day, when Dalton was around, they didn't know what a chemical reaction was, or a nuclear reaction was. That was good. All right, 2. All atoms of a given element are identical. In other words, all atoms of a given element are alike in mass and other properties. Very similar. Not exactly the same, which we know about isotopes today. We'll talk about that later on. Atoms of a given element are different from those of another element. So, like, here's an example. Maybe, I don't know what that is. Maybe the red generally represents oxygen. So let's say that that's hydrogen. Okay. So they're very different. Number 4, atoms of one element can combine with atoms of another element to form compounds. Okay. We know that's true. This would be a weird world with no compounds and only elements. A given compound always has the same relative number and types of atoms. So here we have a water molecule. Looks like Mickey Mouse. We'll talk about that later on when we do Vesper. Or at least the head, sorry, of Mickey Mouse. Number 5. Atoms are indivisible in chemical processes, which was stated earlier. That is, atoms are not created or destroyed in a chemical reaction or process. So a chemical reaction simply changes the way the atoms are grouped together, how they're arranged, how they're with something else. And when they get with something else, just like you change. Okay? It's kind of like when you're with your friends, you behave a lot more, or you behave differently than when, say, you're with your parents or even your grandparents. Okay? I also like to put it where you behave differently in a mall than you would, say, in a church or a synagogue. Okay? At least you should. Okay? So that's the way that elements behave as well. According to Dalton's second law, the ratio of the masses of one element that combine are consistent with the mass of another element, it can be expressed in whole numbers. That's what the law of definite proportions is getting to. Subatomic particles, make sure that we know these. We don't talk about quarks in here. We leave the quarks up to the physicists. All that theory type stuff. Things that we know for sure, electrons, protons, and neutrons, that's what chemists deal with. So make sure that you know what the symbol is, the electron with the negative sign, the proton with the positive sign, the neutron with the neutral sign. And then know the charges, know the relative masses. We do not need to know the actual mass. That is not a concern of ours. All right. So don't sit there and think, do I have to memorize that? No. Okay. No. No, we don't need to memorize it. But I do want you to know that a proton weighs about the same as a neutron. Now it says it's exactly the same here, but I think a proton's a little heavier. Not by anything. Imagine. When we look at an electron, it is very, very light compared to a proton or neutron. That's why we often ignore the mass, and the key is ignore the mass of an electron when we do mass calculations, which we'll do today. All right, atomic number. When we talk about atomic number, if you look on your periodic table, that is the number that's on top. That represents the number of protons. That number is really important because that number does not ever change with an element. As long as we have, say, 6 protons, we're looking at carbon. If we have something that has, say, 29 protons, we're looking at copper. The number of protons identifies what you're looking at. Okay, that's what that statement there is saying. The isotope is the same atom, but it has different numbers of neutrons. So when you hear me refer to, say, like neon 20 or neon 22, okay, the neon tells everybody that, hey, this atom has 10 protons. How do I know that? Because I went to my periodic table and it told me so. The number here at the end is the mass number. And the mass is equal to the protons plus the neutrons. So if we know how many protons an atom has, we can easily find out how many neutrons it has. Because again, neon will have 10 protons. If it has a mass of 20, that tells me that there must be 10 neutrons. And we'll get to do some of those calculations here shortly. Let me also say that the mass number that I will be giving you will not be the same mass number that's on your periodic table. Let me pop that periodic table up here. here. Maybe I don't have it on there. Let's go to Unit 2. I know I had it in Unit 2. Oh, I'm on it already. Perfect. Okay. So when we look at the periodic table here, okay, and what I don't want you to do is go crazy and say, oh, Mr. Craig, when you talk about writing this out, notice that the number here on top represents the number of protons. That's the atomic number. The atomic mass does not have a whole number for the most part. There's only like 2, oxygen and fluorine, and that's really rare. If you notice everybody else has a decimal place value, I mean, I can circle everybody but those 2. These are the average of all the isotopes that exist in the universe, all right? And you'll get to do some calculations to actually find out what those values are. Okay? So the mass numbers that are showing up here are not the same that we're going to have in our examples today. And honestly, we will not use these values until next unit. Okay? So don't sit there and look at the periodic table and go, well, Mr. Craig, you gave me neon, and it's not 20, it's 20.18. No, we don't have a part of a proton or a neutron for what we're doing. Okay? All right, so let's go back. Okay. Go away. Come on over. Maybe not. Oh, I'm back. Maybe. All right. So make sure that we understand what the protons and neutrons are. Okay. Now, you may want to highlight this area right here. The number of protons determines the identity of the element. The number of neutrons determines the particular isotope. Okay. Protons identifies the element. Neutrons identifies the isotope. The mass number that's on the periodic table, again, is the average of all the protons and neutrons for that sample. Now, this table right here actually represents, like for hydrogen, helium, carbon, oxygen, chlorine. It doesn't show everything, but it actually shows the actual breakdown of these isotopes. Like for hydrogen, the majority of hydrogen is hydrogen 1. There's a very, very small percent that's hydrogen 2. I mean, it's less than 1%, which is 0.15. And then hydrogen 3, there's a really, really small percentage. And so on and so forth. So this is the values that I would give you for you to determine what the atomic mass is. Now, how do you do that? That's a good question. Let's try one. Okay. Here's how, or let me ask you. Here I've given you a set of data, okay, where I've got different isotope masses and their respective percentages. How would you go about and find the average? What's a way? Just add all 4 of them up, divide by 4? Never do that. Why? If you were to do that, what would all of these have to be? The same. They'd all have to be 25% in this case. Okay. So for that to take place, they would all have to be equal. Now, some of you have graded weighted grades. Sorry. This class is a weighted class. In other words, the tests are worth more than the quizzes. The quizzes are worth more than the homework in the labs. So when you look at the total number of points, if you were to look at the total number of points and say, hey, I don't get the same percent as you, it's because the grades are weighted. So when we look at those, okay, what we really want to do is this. And this saves a step. I take the decimal and I move it 2 places to the left. Take the decimal, move it 2 places to the left in all of these. And then I'm going to multiply my isotope mass by my new value. Okay? So let me do that real quick. And I'm going to write these values down here. So the first one is 12.3043. The second one is 0.5548. The third one is 7.305. And the last one is 56.2926. Now, we don't want to round these values because whatever we get is what we get. And then once I have these numbers here, add them up. Add those up. And when I add all these together, I get 76.4567. Okay. Now, whenever you get an answer, always evaluate your answer. Ask yourself, does that answer make sense to what we're looking for? Okay. First check. Is it between 71 and 78? And shouldn't our average be between 71 and 78? Yeah. So, okay, so we're looking good so far. Which of these values had the highest percentage? 78, right? So that means that our answer should be closer to 78 than 71. Everybody understand what I'm doing there? Okay. So when you evaluate your answer, do a couple things. First of all, check and make sure that they're actually between the high and the low. If it's not between the high and the low, I guarantee you that you did something goofy over here. Okay. And then look at where it's heaviest or where the percentage is highest. Now, if they're relatively the same, then it probably will be more toward the middle. Okay. Questions on that? And you'll get some more practice with this tonight or today. Fine, be that way. Just keep up with me. Goodness. All right. All right. Find the number of neutrons in an atom. Again, we know the mass number. The mass number has protons plus neutrons. The atomic number is the number of protons. So we can take the difference of those two values and get your number of neutrons. When an atom is neutral, what does that mean, neutral? No charge. Okay. And protons have what charge? Positive. Electrons have negative. Neutrons have no charge. So we're only looking at protons and electrons. If I have, say, a neutral atom, and say I'm looking at carbon that has 6 protons, how many electrons should I have if it's neutral? Perfect. Awesome. Begin the game. Cations, or some say cations, they're not cations. Okay, they're cations. Remember, cats are very positive creatures. Okay, they do exactly what you ask them to. If you throw a stick, they'll fetch it and bring it back to you. When you say sit, they sit. They do exactly what you ask them to do. So that's why they're very positive in their nature, so to speak. Okay. Now, the reason why they're positively charged is because they lose electrons. Lose electrons. Okay. So remember, the number of protons will not change for that element. It's the electrons that can come and go. Okay. If we're looking at, say, anions are negatively charged, and it likes to gain electrons. Okay. And become negative. And then the atoms are ordered on the periodic table based on increasing atomic number. What's the atomic number again? Protons. There we go. Testing you there. All right. And again, the average that you see for the atomic mass on the periodic table deals with the average of all the isotopes. All right. Now, the proper way to write. No. Stay there. Come on. Slide with me. The proper way to write a symbol, okay, looks like this. And you might say to yourself, but Mr. Craig, when I look at the periodic table, the atomic numbers on top. Here are the atomic numbers on the bottom. Here are the atomic numbers on the bottom. Okay, this is the way that chemists represent individual elements. And I'm talking about one atom, not all of the atoms. Okay? So when you look at a single atom, this number right here represents the number of protons plus neutrons. And this number right here represents what again? Protons. Good. So if I want to find the neutrons, I take protons plus neutrons and subtract it from protons. Pretty cool. What you don't see on here is the charge for the element. In this case here, since there was no number there, or if there's a 0 there, that represents that it's neutral. Okay. So if you see no number, we're going to say that the protons equal the electrons. So let me ask you this. Okay. Looking at potassium 39, how many protons does it have? 19. Good. How many neutrons does it have? 20. Good. So take the difference between the two. So we have 20. And in this neutral potassium, how many electrons? 19. Very nice. Okay. Now let's mix it up a little. Potassium loves to give away electrons. And it generally will have a +1 charge. Okay? So if potassium has a +1 charge, let's go through that again. How many protons does it have? 19. Same. How many neutrons? 20. How many electrons? 18. Okay. This is what we call Plainfield math. When you add, you're actually subtracting. Okay? So remember, the proton number doesn't change. So if protons have a positive charge and the overall atom has a +1 charge, that means we have more protons than electrons. So the actual number of electrons should be 1 less than our 19, which in this case is 18. Okay? Remember, if it's positive, we subtract. If it's a negative, then we add. Okay? Let's do another. Chlorine, I think it's number 17. Let's say it's got a 36, and it likes to have a -1 charge. Okay? So let's do this. That's a plus sign. And electrons. So how many protons does chlorine have? All of them do. Good. How many neutrons in this example? Good. And how many electrons? There you go. Very good. 18. Because again, that -1 means that I have 1 more electron than I do proton. Okay. Isn't that fun? Sure. You guys have gone for 3 days, and sure is all I can get out of you. All right. So let's try some here. All right. So, and we should be able to go fast. And again, keep in mind, if there's nothing here, assume it to be neutral. Okay. When you do see a charge, then respect the charge. All right, so how many protons in sodium 24? Again, sodium is identified by the number of protons. What's that? Oh, how many neutrons? 13. How many electrons? Because there's no charge. Good. In arsenic, 76, how many protons? There you go. How many neutrons? How many electrons? There you go. Okay. Looking at sodium, 20 with a +1 charge, how many protons? How many neutrons? 9. And again, it's due to the isotope. How many electrons? 10. Everybody agree with that? I heard 12. It's 10. So again, if it's a +1, that means that we're taking an electron away. Okay. Not a proton, an electron. Okay. All right. Looking at this arsenic, how many protons? How many neutrons? what? 44? Okay. And how many electrons? There you go. Looking at chromium. Uh-oh. So you got to go to the periodic table because, again, the number of protons identifies what you're looking at. So chromium has what number? There you go. So sometimes I might give you, or not give you that, but just go to the periodic table. Sometimes I might do something like that and say, well, what is that mystery element? We don't care right now. How many neutrons? 30. There you go. And how many electrons? 21, because we have 20, and it's probably not a bad idea to put that in there. So since it's a plus 3, we take 3 electrons from the original, which is 21. Good. Do we need to know what this is? No, we don't. So don't go rack your brain and go crazy and go, ah. If you want to know, what is it? Cobalt. Yeah, good. Okay, you don't need to know that. No, copper's 29. Come on now. Oh, sorry. Copper's Cu. All right, so how many protons? 20. How many neutrons? How many? 32. And how many electrons? There you go. And then last but not least, how many electrons or protons? How many neutrons? And electrons? There you go. Sound good? Okay, the homework is the ones today.